So let us we solve this problem by taking the device by device. The first device is called the diffuser, that is A201. Here they gave the Mach number value, that is the ambient Mach number, Ma is equal to 0.75, and they also mentioned it comes under the sea level conditions. We already know that for sea level condition we have some constant pressure as well as the constant temperature, that is Pa is equal to 101.3 kilonewton per meter square and Ta is equal to 288 Kelvin. Now Ma is equal to Ca divided by root of gamma RTA. By substituting the Mach number value, gamma value, R value, that is 287 joules per kg Kelvin, and the constant temperature value 288, and solving Ca, will get Ca is equal to 255.130 meter per second. Also we know that your stagnation temperature T01 is equal to Ta plus Ca square divided by 2Cp. We know that the Cp value is constant. For the air, it's 1005 joules per kg Kelvin. By substituting the Ta value and Ca square as well as the Cp value, will get T01 is equal to 320.383 Kelvin. This is the diffuser values. As well as we know the isentropic relation, that is P01 by Pa is equal to T01 by Ta power gamma divided by gamma minus 1. By substituting the Pa value and T01 and Ta values as well as the gamma value and solving P01, will get P01 is equal to 147.088 kilonewton per meter square. The next one is that called compressor, that is 01202. Here they gave the compressor pressure ratio, that is P02 divided by P01 is equal to 15. Already we found the value of P01 in the diffuser. So therefore by substituting the P01 value in the compressor pressure ratio and solving P02, we will get P02 is equal to 2206.32 kilonewton per meter square. The next one is that to find out the T02 value. So that is what we may go for the isentropic relation, that is T02 divided by T01 is equal to P02 divided by P01 whole power gamma minus 1 divided by gamma. Again by substituting the T01 value as well as the pressure ratio value and solving T02, will get T02 is equal to 694.537 Kelvin. The next device is called the combustion chamber. In this problem they gave the combustion chamber exit temperature T03 is equal to 1389 Kelvin, as well as already we know that this combustion chamber comes under the constant pressure process. In ideal turbojet engine, there is no pressure losses in this chamber. So therefore your P03 is equal to P02 is equal to 2206.32 kilonewton per meter square. So why it comes under the constant pressure? Means it's a constant pressure without any losses, that is the frictional losses. Also in the combustion chamber we have to find out the mass rate of fuel. So therefore we may go for the energy balance equation. We know that the heating value of fuel QR is equal to the ratio between mass rate of air to the mass rate of fuel into Cp into delta T. The delta T is nothing like that, the temperature difference. So therefore we may put QR is equal to Ma divided by Mf to Cp into T03 minus T02, that is the maximum temperature minus the minimum temperature. So Ma is nothing like this, a mass rate of fuel, and Mf is a mass rate of Ma is mass rate of air and Mf is a mass rate of fuel. By substituting the heating value of fuel as well as the remaining Ma, Cp as well as the temperature values and solving Mf, will get the mass rate of fuel, which becomes 1.261 kg per second. Comparatively, the mass rate of fuel value is very low than the mass rate of air. In ideal turbojet engine, the air to fuel ratio becomes 100:1. So we notice that your mass rate of fuel value is very lower than the mass rate of air. The next one is that called the turbine. Here I have mentioned the turbine work done is equal to the compressor work done. How it comes? Already I have mentioned the turbine which is used to operate the compressor by connecting a shaft, that is the same shaft. So that is what, whenever the turbine works, your compressor also works. So therefore your turbine work done is equal to the compressor work done. Then modernly we know that the turbine work done is equal to mcp into delta t, as well as the compressor work done is mcp into delta t. For turbine we have the maximum temperature of T03 and the minimum temperature of T04, and the compressor we have a maximum temperature of T02 and the minimum temperature of T01. By cancelling the MCP in both sides, will get T03 minus T04 is equal to T02 minus T01. Again, by substituting the T03 value, T02 value and T01 value and solving T04, you will get T04 is equal to 1014.846 Kelvin. As well as by using the isentropic relation, your P04 divided by P03 is equal to T04 by T03 whole power gamma divided by gamma minus 1. Again, substituting the P03, T04 and T03 values and solving P04, we'll get P04 is equal to 735.548 kilonewton per meter square. The next device is called the nozzle. So before elaborately going to solve this one, we need to know your static pressure, that is the PA is equal to P5, that is your entry pressure is equal to exit pressure. So for ideal condition, your PA is equal to P5 or PE, that is your ambient pressure is equal to the exit pressure. So let us take PA is equal to P5 is equal to 101.3 kilonewton per meter square. Again, coming to the isentropic relation, T04 divided by T5 is equal to P04 by P5 whole power gamma minus 1 by gamma. Substituting all those values, that is T04, P04 and P5, will get T5 is equal to 575.969 Kelvin. Also we know that the temperature ratio, that is T04 divided by T5 is equal to 1 plus gamma minus 100 by 2 into M5 square. And by substituting all the values other than the M5, will get M5 is equal to 1.951. As well as we know that M5 is equal to C5 divided by root of gamma or T5. Again, your M5 value is 1.951. It's absolutely a supersonic value. And C5, it's an unknown value. And substituting the gamma is 1.4, R value is 287, and T5 is 575.969. Will get C5 is equal to 938.559 meter per second. So we found all the values of pressures and temperatures simultaneously the velocities. Now coming to the thrust, they are actually asked the thrust. So therefore the thrust is nothing like that, it's a addition of pressure thrust and a momentum thrust. So the pressure thrust is nothing like that, it's a product of pressure into area. That is, here I have mentioned your exit pressure minus inlet pressure into the exit area. As well as the momentum thrust is nothing like that, it's a mass flow rate into velocity. That is what I have mentioned here, mass flow rate of air into exit velocity minus inlet velocity, that is the ambient velocity. In the previous slide I have mentioned your exit pressure is equal to the ambient pressure. So therefore your P is equal to P5 and C is equal to C5. Ideally we have taken, for the ideal condition we have taken that P is equal to PA. Whether the P is equal to PA, your pressure thrust will becomes 0. So therefore we have only the momentum thrust. So therefore F is equal to MA into CE minus CE. So by substituting the mass rate of air value and the exit velocity and the inlet velocity, will get thrust value is 51140.992 Newton. The next one is called TSFC, that is thrust specific fuel consumption. Here the thrust specific fuel consumption is the ratio between mass rate of fuel to the thrust. So by substituting the mass rate of fuel, that is 1.261 by thrust value multiplied by 3600. Why I have mentioned here the 3600 means we need to convert the value of specific fuel consumption value in seconds to the hour. That is what I need to multiply this value by 3600. Will get TSFC is equal to 0.08876 kg per hour Newton. Thank you.